Look up at the night sky, and you're not just seeing stars. You're staring at the universe's grandest equation, written in the language of numbers. Every spiral galaxy, every cluster of cosmic webs, even the vast voids between them, they all follow patterns so precise. It's as if the cosmos is counting, calculating, constructing itself according to some hidden arithmetic. What if the universe isn't just governed by math, but is math? What if the very fabric of reality is solving problems we're only beginning to grasp? This is the mystery of cosmic arithmetic, the strange, beautiful rules that shape everything from the tiniest atoms to the largest structures in existence. For centuries, humans have sensed this hidden order. Ancient astronomers traced the paths of planets and saw geometric perfection. Philosophers like Plato imagined the universe built from pure mathematics triangles and spheres as the blueprints of reality. Even today, when we peer through telescopes, we find the same numbers echoing across the cosmos. The golden ratio in the swirl of galaxies, the unshakable presence of pi in the curves of black holes, the Fibonacci sequence unfolding in hurricane clouds and galaxy arms alike. It's as if the universe left a trail of numerical breadcrumbs for us to follow. But why? Is this just a coincidence, or is there a deeper logic waiting to be uncovered? That's the journey we're embarking on today. A voyage from the earliest whispers of numerology to the cutting edge of astrophysics, where scientists are decoding the universe like a cryptic love letter written in equations. We'll explore how prime numbers might hold the key to galaxy clusters, why the vacuum of nothingness is secretly bursting with energy, and whether the cosmos itself could be a cosmic calculation running on laws we haven't fully cracked yet. This isn't just about math or science, it's about the awe of realizing that the universe might be more than a place. It could be a puzzle, a poem, even a proof. And you're part of the story, so let's begin. Long before telescopes or supercomputers, ancient civilizations gazed at the night sky and saw more than just scattered stars. They witnessed a celestial symphony playing out in perfect numerical harmony. The Babylonians, meticulous astronomers of Mesopotamia, tracked the movements of planets with such precision that they could predict eclipses centuries in advance. But to them, these patterns weren't just observations, they were divine messages, a sacred arithmetic written in the language of the gods. They divided the sky into 12 segments, mirroring their base 60 number system, which still echoes in our 60-minute hours and 360-degree circles. It was as if the heavens themselves were counting. Then came the Pythagoreans, a group of Greek philosophers who believed numbers were the essence of all things. To them, the cosmos wasn't just governed by math, it was math. They discovered that musical notes could be expressed as simple ratios, like the octave vibrating at a 2-to-1 proportion. If harmony on Earth followed these rules, why not the harmony of the spheres? Pythagoras imagined planets orbiting to an inaudible music, their speeds and distances creating a cosmic chord. This idea might sound poetic, but it planted a radical seed. The universe could be understood through numbers. Plato took this further in his dialogue Timaeus, where he proposed that reality itself was built from geometric shapes. Fire was a tetrahedron, earth a cube, air an octahedron, each element a perfect mathematical form. Even the cosmos, to Plato, was a spinning dodecahedron, its faces etched with the stars. While his specifics were off, his intuition was startlingly prescient. Modern physics reveals that the fundamental forces of nature do rely on geometric principles, from the symmetry of atoms to the curvature of spacetime. Centuries later, Johannes Kepler became the bridge between ancient mysticism and modern science. Obsessed with Pythagoras harmonies, he spent years trying to fit the planet's orbits into perfect circles and musical ratios. But the data refused to cooperate until he stumbled upon ellipses. His 3 laws of planetary motion shattered the old ideals, yet revealed something deeper. Math wasn't about perfection. It was about precision. The planets didn't move in divine circles, but in elegant, calculable ellipses, their speeds and positions governed by exact relationships. Kepler's breakthrough was a revelation. The universe didn't care for human ideals of beauty. It had its own logic waiting to be decoded. Today, we see these cosmic numbers everywhere. The golden ratio, approximately 1.618, appears in the spiral arms of galaxies, the branching of trees, even the proportions of our own DNA. Pi, the endless number representing the ratio of a circle's circumference to its diameter, shows up in the ripples of the cosmic microwave background, the faint afterglow of the Big Bang. These aren't just curiosities, they're clues. The universe seems to be whispering that beneath the chaos of stars and galaxies, there's an order, a structure, a set of rules written in the only language that transcends time and space, mathematics. Take a sunflower and count the spirals in its seed arrangement. You'll likely find 21 winding clockwise and 34 counterclockwise, 2 consecutive numbers in the Fibonacci sequence, where each number is the sum of the 2 before it. This same pattern appears in pine cones, pineapples, even the branching of trees, but it doesn't stop there. Look up at a hurricane from space, and you'll see its swirling clouds forming a spiral that echoes those sunflower seeds. And when astronomers point their telescopes at the Whirlpool galaxy, they capture something astonishing. Its vast, luminous arms twisting in a near-perfect logarithmic spiral, a shape that grows wider by a factor of the golden ratio with each turn. Why does this sequence 1, 1, 2, 3, 5, and so on show up so relentlessly from the microscopic to the cosmic? The answer lies in efficiency. In sunflowers, the Fibonacci arrangement allows each seed to pack tightly without crowding, maximizing space and sunlight. For hurricanes, the spiral distributes energy in a way that balances rotation and expansion. And galaxies, their arms are shaped by the same principle of optimal flow, where gravity and motion conspire to create these elegant curves. It's as if nature has a favorite blueprint, a mathematical recipe for building structures that waste nothing. But is this just a happy accident? Some scientists argue these patterns emerge from simple physical laws, like how a soap bubble naturally forms a sphere to minimize surface tension. Others see something deeper, a hidden order, a universal preference for certain ratios that balance growth and stability. The golden ratio, closely tied to Fibonacci numbers, appears in the proportions of galaxies, the spacing of planets, even the vibrations of stars. When the same numbers keep surfacing across scales, it's hard to dismiss as mere coincidence. Then there's the question of what this means for our understanding of reality. If the universe repeatedly converges on these patterns, does it suggest an underlying optimization, a kind of cosmic economy where energy and matter arrange themselves in the most efficient way possible? Or could it be evidence of something even more profound, a mathematical fabric woven into the very laws of physics? The Fibonacci sequence might just be a clue, a hint that the universe isn't just governed by numbers, but that it thinks in them. And if that's true, what other equations are waiting to be discovered in the spiral of a galaxy or the curl of a fern? Pi is more than just a number we memorize in school. It's a silent architect of the cosmos, hiding in the curves of planets, the whirl of galaxies, even the edge of oblivion itself. Take something as simple as a planet's orbit. The time it takes for a world to circle its star isn't random. It's governed by a precise mathematical relationship involving pi. Kepler's third law ties a planet's orbital period to its distance from the Sun, and right there, nestled in the equation, is pi, a proof that the universe measures its dance in this irrational, infinite constant. But pi's influence goes far beyond orbits. When Einstein rewrote our understanding of gravity with general relativity, he described spacetime as a flexible fabric, warped by mass and energy. The equations that define this curvature, they're laced with pi. Every black hole's event horizon, the point of no return where even light can't escape, has a circumference calculated by 2 pi times its radius. It's as if the universe uses pi as a cosmic seamstress, stitching the very geometry of reality. Then there's the cosmic microwave background, the afterglow of the Big Bang. This faint radiation, the oldest light we can see, carries tiny temperature fluctuations, hot and cold spots that map the early universe's density. When scientists analyze these patterns, they find something astonishing. The distribution of these fluctuations follows a statistical curve where pi appears again. It's like finding the same signature on the universe's birth certificate and its grown-up structures. So why does pi show up everywhere? Some argue it's inevitable, the natural result of describing anything circular or spherical in a three-dimensional universe. Others wonder if it's a clue to something deeper. After all, pi isn't just about circles. It pops up in equations describing probabilities, waves, even the distribution of prime numbers. Could pi be more than a mathematical tool? Could it be a fundamental thread in the tapestry of reality, woven into the laws that govern everything from atoms to galaxies? The mystery deepens when we consider that pi is irrational. Its digits never repeat, never end. It's a number that defies containment, much like the universe itself. Maybe that's the point. If the cosmos is infinite, perhaps it needs an infinite number to describe it. Or maybe pi is a bridge connecting the simplicity of a circle to the complexity of existence, reminding us that even in the chaos of the cosmos, there's an order, one that we're only beginning to decode. The golden ratio, 1.618, is a number so elegant it seems to whisper secrets about beauty, balance, and the hidden order of things. Artists like Leonardo da Vinci embedded it in the Mona Lisa's enigmatic smile. Architects designed the Parthenon's columns to mirror its proportions. Even seashells and hurricanes spiral outward in its precise increments. But this isn't just an earthly obsession. Look deep into space, and you'll find the same ratio etched into the cosmos itself. Quasars, the blazing hearts of distant galaxies, have been observed to cluster at distances that align with the golden ratio. Galaxy superstructures, those vast filaments of matter stretching across the universe, sometimes repeat this proportion like a cosmic fingerprint. How does this happen? One theory points to fractals, patterns that repeat at every scale. Imagine a tree branch splitting into smaller branches, each division echoing the one before it. The universe might build itself the same way. When researchers analyzed the distribution of galaxies in the Sloan Digital Sky Survey, they found clusters spaced at intervals close to the golden ratio, as if space itself were following an invisible blueprint. Some mathematicians argue this isn't random. They see it as evidence of a deep structural law, a preference for efficiency and stability woven into the fabric of reality. But not everyone's convinced. Skeptics counter that our brains are wired to seek patterns, even where none exist. If you look hard enough, you can find the golden ratio in anything, from stock market charts to the shape of a banana. Could the same be true in astronomy? Astrophysicist Neil Turok once quipped, "The universe is under no obligation to impress us with its symmetry. Yet the sheer frequency of this ratio, from microscopic algae to galactic arms, is hard to dismiss as mere coincidence. The debate splits scientists into two camps. One side, led by researchers like Mario Livio, argues the golden ratio emerges from fundamental physics, a natural outcome of systems seeking optimal growth or energy distribution. The other side, championed by skeptics like Ethan Siegel, insists it's a classic case of apophenia, seeing connections that aren't there. The universe is messy, Siegel warns. If you cherry-pick data, you'll always find pretty numbers. So who's right? The answer might lie in the math itself. The golden ratio appears in solutions to the Fibonacci sequence, which governs growth patterns across nature. It's also tied to the geometry of pentagons and dodecahedron shapes that emerge in everything from quantum crystals to the large-scale structure of spacetime. Whether it's a universal law or a cosmic mirage, one thing's certain: the golden ratio keeps pulling us deeper into the mystery of why the universe seems to count, measure, and build itself this way. And that's a puzzle worth solving. Prime numbers, those elusive integers divisible only by 1, and themselves seem like pure mathematical abstractions, the kind of thing you'd expect to stay confined to textbooks or encryption algorithms. But look closely and you'll find them lurking in the most unexpected corners of the universe. Take quantum mechanics. The energy levels of electrons in an atom don't just follow any random pattern. In certain systems, like the hydrogen atom, these energy states correspond to prime numbers. It's as if the microscopic world is counting in primes, organizing itself according to an arithmetic rulebook we're only beginning to decipher. Then there's the large-scale structure of the cosmos. Astronomers mapping galaxy clusters have noticed something peculiar. The distances between these colossal formations aren't entirely random. When you analyze the spacing, certain intervals recur more often than chance would predict, and those intervals, they frequently align with prime numbers. It's as if the universe, when building its grandest structures, consulted a checklist written in primes. This eerie connection between primes and physics becomes even stranger when you examine the Ulam spiral. In the 1960s, mathematician Stanislaw Ulam was doodling during a lecture, idly numbering integers in a spiral on graph paper. When he circled the primes, something astonishing emerged. Instead of scattering randomly, the primes clustered along diagonal lines, forming intricate geometric patterns. These weren't just visual quirks, they hinted at a hidden order governing primes, one that mathematicians are still untangling today. What's truly mind-bending is how these prime-generated lines resemble the cosmic web, the vast network of galaxies and dark matter stretching across the universe. Both exhibit a kind of structured randomness where patterns emerge from chaos without any obvious guiding hand. Could primes be more than just numbers? Could they be the universe's way of building complexity from simplicity? A set of cosmic Lego blocks that assemble everything from atoms to galaxies. Number theorists like Terence Tao have spent careers probing primes' secrets. Tao's work on prime gaps, the spaces between consecutive primes, reveals that these numbers, though infinite, follow subtle statistical rules. They're not entirely lawless, and if primes underpin both quantum physics and galactic architecture, it raises a tantalizing question. Is there a universal algorithm, a primal code that shapes reality at every scale? Skeptics argue that finding primes in nature might just be selective perception after all. Primes are everywhere in math, so spotting them in the wild isn't surprising. But the sheer ubiquity of these patterns, from the quantum realm to the cosmic web, suggests something deeper. Maybe primes aren't just tools for counting or cryptography. Maybe they're woven into the fabric of existence itself, silent architects of a universe that's far more mathematical than we ever imagined. Zero is more than just a placeholder in our number system, it's a cosmic riddle, a concept so powerful that it reshaped mathematics, philosophy, and even our understanding of reality itself. Its journey begins in ancient India, where astronomers and mathematicians like Brahmagupta first dared to give nothingness a name and a symbol. Before zero, the idea of an empty quantity was unthinkable in many cultures. How could you count what wasn't there? But the Hindus saw deeper. They recognized that zero wasn't just an absence, it was a boundary, a fulcrum balancing positive and negative numbers, a tool that unlocked the very possibility of algebra and calculus. Without zero, modern science as we know it wouldn't exist. Yet zero's true paradox lies in physics, where nothing is anything but empty. Take the vacuum of space, a realm we once imagined as pure void. Today, quantum mechanics reveals it as a seething foam of virtual particles, flickering in and out of existence in fractions of a second. This quantum foam isn't just theoretical. It's measurable. The Casimir effect, where two metal plates placed nanometers apart in a vacuum inexplicably pull toward each other, proves that even in the absence of matter, energy thrums beneath the surface. Zero, it turns out, is a hive of activity. This bizarre behavior ties directly to the universe's most profound mystery. Why does anything exist at all? According to quantum field theory, the net energy of the cosmos might actually be zero. How? Every particle of matter has positive energy, but gravity, the curvature of spacetime, carries negative energy. Add them together and the sum might cancel out to nothing. In other words, the universe could be the ultimate free lunch, a cosmic balancing act where zero begets everything. But zero's paradox doesn't stop there. In black holes, the gravitational pull is so intense that not even light can escape. At their cores, equations predict a singularity, a point of infinite density where spacetime itself breaks down. And yet, mathematically, a singularity is also a zero, a place where our understanding hits a wall. It's as if zero is both the origin and the limit of reality, the silence between notes that defines the music of the cosmos. From the Big Bang's fiery birth, where zero-dimensional points exploded into a universe, to the quantum vacuum's ceaseless creativity, zero is the silent architect of existence. It's the void that shapes galaxies, the nothingness that spawns particles, the blank page on which the universe writes its story. And perhaps that's the greatest lesson zero teaches us, that emptiness isn't an end but a beginning. The cosmos, it seems, counts its greatest wonders from nothing. Infinity isn't just an abstract idea, it's a cosmic curveball that keeps throwing our understanding of the universe into chaos. Take black holes, those gravitational monsters lurking in space. At their cores, equations predict a singularity, a point where density becomes infinite, space-time curvature goes off the charts, and the laws of physics as we know them simply give up. But how can something be infinitely small, infinitely dense? It's like the universe is dividing by zero, a mathematical paradox that leaves even the brightest minds scratching their heads. This isn't just a black hole quirk. The Big Bang theory suggests our entire universe might have begun from an infinitely hot, infinitely dense singularity. Yet here's the twist: infinity isn't a number you can plug into real-world calculations. When equations spit out infinities, it's often a sign that our models are incomplete, that we're missing a crucial piece of the puzzle. Physicists call these singularities not because they're rare, but because they're places where the math singularly fails to describe reality. Enter Hilbert's Hotel, a thought experiment dreamed up by mathematician David Hilbert to illustrate how infinity bends logic. Imagine a hotel with infinitely many rooms, all occupied. A new guest arrives, and here's the trick. You ask everyone to move one room over. Room 1 moves to 2, 2 to 3, and so on. Suddenly, room 1 is vacant, even though no one left. Now imagine infinitely many new guests arriving. No problem. Just shift everyone to double their current room number, freeing up all the odd-numbered rooms. In an infinite universe, the rules of everyday arithmetic no longer apply. You can add, subtract, even multiply infinity, and it stays stubbornly infinite. This bizarre property has startling implications for cosmology. If space is truly infinite, as some measurements of the cosmic microwave background suggest, then somewhere out there, an exact copy of you might be reading this very script in a galaxy identical to ours. Not just similar, but atom for atom identical. In an endless cosmos, every possible configuration of matter must repeat eventually. It's not science fiction, it's the logical outcome of infinity. Multiverse theories take this even further. Inflationary cosmology proposes that our universe is just one bubble in a frothy sea of eternally expanding space, where new universes constantly bud off with different physical laws. In this multiverse, infinity isn't just about size, it's about possibility. There could be universes where gravity is stronger, where time runs backward, or where pi equals exactly 3. When you have infinite universes, every conceivable outcome must exist somewhere. But here's the catch: can we ever prove it? Infinity operates beyond the reach of observation or experiment. Some theorists, like Max Tegmark, argue that if a multiverse exists, it must contain every mathematically possible structure by definition. Others, like physicist Paul Steinhardt, counter that untestable ideas, no matter how elegant, stray from science into metaphysics. The debate cuts to the heart of how we understand reality. Is the universe a single, finite system we can comprehend, or is it an infinite mosaic, forever beyond our grasp? Perhaps the most unsettling thought is this: if infinity is real, then everything we cherish, every star, every civilization, every moment of joy or sorrow, becomes statistically insignificant in an endless sea of repetition. Yet somehow, that very vastness makes the fact that we're here to ponder it all the more extraordinary. Infinity doesn't just challenge our equations, it forces us to confront what it truly means to exist in a cosmos without end. Imagine looking at a galaxy spinning so fast that its stars should fling outward like riders on a cosmic carousel gone haywire, yet they don't. They cling to the edges, defying gravity's expected rules. This cosmic sleight of hand has a name: dark matter. It's the universe's phantom limb, invisible yet exerting a gravitational grip so strong it shapes the fate of galaxies. We can't see it, touch it, or even detect it directly, but we know it's there because without it, the math of the cosmos simply doesn't add up. Dark matter isn't some minor player, it's the scaffolding of the universe, making up roughly 27% of everything that exists. Ordinary matter, the stuff of stars, planets, and us, a mere 5%. The rest is an even more enigmatic force called dark energy, but that's another story. For decades, scientists have pieced together dark matter's presence through its gravitational fingerprints. When galaxies rotate, their outer stars move far quicker than Newton's laws predict. The only explanation: an unseen mass wrapping around galaxies like an invisible cocoon, tugging stars into obedient orbits. But here's where it gets stranger. Recent supercomputer simulations, like the groundbreaking work from projects like Illustris TNG, reveal that dark matter doesn't just lurk in halos around galaxies. It forms an intricate cosmic web, a labyrinth of filaments and knots stretching across the universe, with galaxies clinging to its threads like dew on a spider's silk. Even eerier, this web isn't random. When researchers zoom in, they find patterns reminiscent of fractal geometry, where the same shapes repeat at smaller and smaller scales. It's as if the universe is running a recursive algorithm with dark matter as its hidden code. The hunt to crack this code has led to some wild theories. Could dark matter be made of primordial black holes forged in the chaos of the Big Bang? Or is it a sea of undiscovered particles like WIMP, weakly interacting massive particles that barely whisper to ordinary matter? Experiments deep underground in abandoned mines and mountain tunnels search for these elusive particles shielded from cosmic noise, so far silent. But the absence of answers only fuels the mystery. Perhaps the most tantalizing clue lies in the anomalies. Some galaxies, like NGC 1052, seem to have almost no dark matter at all, throwing a wrench into the prevailing theories. Others, like Dragonfly 44, are 99.99% dark matter, barely a flicker of stars in a sea of shadow. These outliers suggest dark matter isn't just a uniform glue, it's dynamic, maybe even alive in ways we don't yet understand. One thing's certain, dark matter is more than a missing variable in an equation. It's a cosmic question mark, a reminder that the universe still holds its cards close. Every time we think we've glimpsed the rules, the cosmos laughs and deals another hand. And somewhere in that cosmic deck lies the answer not just to what dark matter is, but to how the universe truly counts. If dark matter is the universe's unseen scaffolding, dark energy is its mysterious engine, an invisible force not just expanding the cosmos, but doing so at an ever-increasing speed. Picture a baker adding yeast to dough, watching it rise. Now imagine the dough suddenly doubling in size, then quadrupling faster and faster without extra yeast. That's the enigma of dark energy, a cosmic accelerant making up roughly 68% of the universe's total content, dwarfing even dark matter. And here's the kicker, we have no idea what it actually is. This story begins with Einstein's greatest blunder. In 1917, his equations for general relativity suggested the universe should either expand or collapse. But the prevailing belief at the time was a static, unchanging cosmos. So Einstein introduced a fudge factor, the cosmological constant, a mathematical term that counteracted gravity's pull, keeping the universe balanced like a house of cards in perfect equilibrium. When Edwin Hubble later proved the universe was indeed expanding, Einstein scrapped the constant, calling it his biggest mistake, but the joke was on him. 70 years later, astronomers studying distant supernova made a bombshell discovery. The expansion wasn't just continuing, it was speeding up. The cosmological constant wasn't a mistake after all. It was a prophecy. Today, dark energy is the leading explanation for this acceleration. Think of it as anti-gravity, a repulsive force woven into the fabric of space itself. As the universe grows, more space appears, and with it, more dark energy, creating a feedback loop of runaway expansion. But the cosmological constant is just one possibility. Some theorists propose quintessence, a dynamic energy field that fluctuates over time, unlike Einstein's static constant. Named after the fifth element of ancient philosophy, quintessence could grow stronger or weaker, potentially altering the universe's fate. Then there's the vacuum decay hypothesis, a scenario straight out of a physicist's nightmare. Quantum theory suggests that what we call empty space is actually a seething foam of particles popping in and out of existence. If our vacuum is just a low-energy false state, a quantum bubble could one day nucleate, rewriting the laws of physics at light speed and obliterating reality as we know it. It's speculative, but the math checks out. Dark energy might be the first hint that our universe is fundamentally unstable. The stakes couldn't be higher. If dark energy behaves like Einstein's constant, the universe will expand forever, galaxies drifting apart until the sky goes dark. If it's quintessence, the cosmos might tear itself apart in a big rip. Or vacuum decay could reset everything to zero. Each theory leaves its own fingerprints in the cosmic microwave background, the large-scale structure of galaxies, and the rate of supernova. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are racing to collect clues. What's fascinating is how dark energy forces us to confront the limits of human knowledge. It's not just an invisible force, it's a mirror reflecting how much we still don't understand about the universe's deepest rules. Einstein's mistake might hold the key, or we might need an entirely new physics to crack this puzzle. Either way, dark energy isn't just shaping the cosmos, it's reshaping our quest to decode it. The cosmic microwave background isn't just ancient light, it's a fossilized whisper from the dawn of time, etched with a hidden mathematical language. Picture it like a cosmic barcode, those faint temperature fluctuations, hot spots and cold spots stretching across the sky. But these aren't random, static. They're the universe's first equation, a snapshot of infant cosmos just 380,000 years after the Big Bang, when matter and light finally parted ways. And just like a barcode holds information in its stripes, these fluctuations encode the universe's DNA, the seeds of all structure to come. To crack this code, scientists use a tool straight from a mathematician's playbook, Fourier analysis. Imagine listening to a symphony where every instrument plays a single note at different volumes. Fourier's math lets you disentangle that cacophony, isolating each violin, each trumpet, to reveal the harmony beneath. Apply that to the CMB and something magical happens. Those temperature variations decompose into a spectrum of tones, waves of different sizes and strengths, like musical notes frozen in spacetime. The loudest note corresponds to waves about 1 degree across the sky, a cosmic bass hum left over from gravity's tug of war in the primordial plasma. But here's where it gets profound. These harmonics aren't just pretty patterns, they're blueprints. The hotter spots mark regions where matter was slightly denser, places where gravity would later sculpt galaxies. The colder spots, sparse voids, the future empty stretches between cosmic threads. It's as if the universe was born with a resonant frequency, a preferred scale where matter clumped most efficiently. And that scale matches predictions from quantum mechanics, tiny fluctuations stretched to cosmic proportions by inflation, the universe's explosive growth spurt. The numbers tell a staggering story. When researchers plot these fluctuations on a graph, the result isn't chaos. It's a curve so precise it's been called the music of creation. Peaks and troughs align with theoretical predictions down to a fraction of a percent, confirming that the early universe vibrated like a plucked string. Even more astonishing, the ratios between these peaks reveal the universe's ingredients. How much is ordinary matter? How much is dark matter, even the influence of dark energy? The CMB isn't just a relic, it's a Rosetta Stone, translating the universe's birth cries into equations we can read. What's truly humbling is how this connects to the cosmos we see today. Those microscopic ripples, amplified over billions of years, became the galaxies and voids we observe. The same math that describes a vibrating guitar string also governs the distribution of superclusters. It's a reminder that the universe doesn't just follow rules, it sings them. And every time we map the CMB with greater precision, from Cobe to Planck to next-generation telescopes, we're tuning into that primordial melody, hearing the universe count itself into existence. If you could step outside our galaxy and look back at the universe from a distance, you wouldn't see stars scattered randomly like salt spilled on a table. Instead, you'd behold an immense shimmering web, vast threads of galaxies stretched across unfathomable distances, intersecting at glittering nodes where thousands of galaxies swarm together. Between them, darkness, not the empty black of a moonless night, but true void's regions so devoid of matter that if you stood in one, the nearest galaxy would be too faint to see with the naked eye. This is the cosmic web, the universe's grandest structure, and it's not just beautiful, it's a mathematical marvel. For decades, astronomers assumed galaxies were spread evenly through space. But in the 1980s, redshift surveys began to reveal the truth. Galaxies cluster along filaments like beads on invisible strings, weaving a tapestry that spans billions of light years. The Sloan Digital Sky Survey, one of the most ambitious mapping projects in history, cemented this picture. By cataloging millions of galaxies, it revealed a web so intricate that its filaments trace the same patterns as neurons in a human brain or the foam on a cappuccino, a fractal architecture repeating across scales. The resemblance isn't poetic coincidence, it's physics. These filaments aren't made of galaxies alone. They're highways of dark matter, the unseen scaffolding that dictates where ordinary matter, gas, stars, planets can gather. Simulations show how dark matter's gravity sculpts this web. After the Big Bang, tiny quantum ripples grew under gravity's pull, attracting matter like magnets until the densest regions collapsed into knots, leaving behind tunnels and caverns of near-nothingness. The result, a cosmic sponge where less than 10% of space contains most of the universe's mass. But here's the puzzle. The web's geometry defies simple explanation. Its filaments intersect at precise angles, forming tetrahedral patterns that mirror the bonds in a crystal. Some researchers see this as evidence of an underlying equation, perhaps a quantum fluctuation frozen in spacetime, stretched to cosmic proportions. Others suggest it's emergent, the inevitable outcome of gravity and dark energy's push and pull over billions of years. The most tantalizing clue lies in the numbers. When scientists measure the distribution of galaxy clusters, they find statistical echoes of the cosmic microwave background's fluctuations, as if the universe's first whispers were imprinted onto its grown-up structure. It's like finding the same signature on both a seed and the tree it becomes. Could the cosmic web be the solution to a differential equation written at the dawn of time? Its variables hidden in the interplay of dark matter, dark energy, and the fundamental constants. Or maybe we're asking the wrong question. Perhaps the web isn't the answer to an equation but the equation itself, a living, evolving mathematical entity that the universe is continuously solving. Every filament, every void, every galaxy cluster might be a term in a computation so vast we're only seeing the first few lines. And if that's true, then mapping the cosmic web isn't just astronomy, it's reverse engineering the universe's source code. A coastline viewed from space doesn't follow straight lines or smooth curves. It twists and turns in jagged, intricate patterns that repeat at every scale. Zoom in on a single rocky outcrop, and you'll find the same winding complexity as the entire continent. This is the essence of a fractal, a shape that echoes itself infinitely, where the whole is mirrored in every fragment. And it's not just Earth's geography that behaves this way. The universe itself is written in this recursive language, from the tendrils of interstellar dust to the sprawling architecture of galaxy clusters. Benoit Mandelbrot, the mathematician who coined the term fractal in the 1970s, first noticed these patterns in financial markets and cotton price fluctuations. But his real breakthrough came when he realized that fractals weren't just human-made abstractions, they were nature's default setting. A cauliflower's florets, a river's branching tributaries, even the bronchial tubes in your lungs all exhibit this self-similarity. Then astronomers pointed telescopes at the cosmos and found something astonishing. The same rules apply. The distribution of matter in the universe isn't random. Zoom out from a local cluster of galaxies to the supercluster it's part of, and the same filamentary structures reappear like a Russian nesting doll of cosmic scaffolding. Take the famous Mandelbrot set, the infinitely complex fractal generated by a deceptively simple equation. Its swirling, flame-like borders contain smaller copies of itself ad infinitum. Now compare it to simulations of the cosmic web, the vast network of dark matter and galaxies stretching across the observable universe. The resemblance is uncanny. Both exhibit branching patterns, voids, and dense nodes that repeat whether you're looking at a slice of space 10 million light-years wide or 10 billion. It's as if the universe took Mandelbrot's notebook and scaled it up to galactic proportions. This raises a provocative question. Is the cosmos itself a kind of computation, iterating fractal growth like an algorithm? Some theorists, like physicist Stefan Alexander, argue that the universe might literally be computing its own structure, with physical laws acting as code. In this view, the Big Bang wasn't just an explosion, it was the initialization of a program, setting off recursive processes that generated complexity from simple rules. The fractal patterns we see would then be inevitable, like the spirals in a sunflower emerging from Fibonacci arithmetic, but not everyone's convinced. Skeptics point out that while fractals are useful for describing cosmic structures, that doesn't mean the universe is running fractal code. After all, waves in the ocean follow mathematical patterns too, but nobody suggests the sea is performing calculations. The debate hinges on whether self-similarity is evidence of deeper computational laws or just an elegant metaphor. Yet the evidence keeps piling up. When astronomers analyze the distribution of cosmic dust, the raw material for stars and planets, they find fractal clustering down to scales as small as our solar system. Even the voids between galaxies aren't truly empty. They're frothy with microscopic fluctuations that echo the large-scale web. It's as if the universe is whispering the same secret at every magnification: growth, division, repetition. Whether this points to a computational cosmos or simply nature's love of efficiency, one thing's certain: fractals challenge our intuition about order and randomness. The universe isn't just building complexity, it's doing so with a strange, recursive elegance that feels almost intentional. And if we ever crack the code behind this cosmic self-similarity, we might not just understand how galaxies form. We might glimpse the very blueprint of reality. Symmetry isn't just about pleasing shapes or mirrored butterflies, it's the silent architect of the universe. A hidden rulebook that dictates everything from the spin of electrons to the whirl of galaxies. Take a snowflake under a microscope, and you'll see 6 identical arms radiating from the center, a masterpiece of symmetry so precise it feels almost mathematical. Now zoom out to the cosmos, and you'll find the same principle at work. Spiral galaxies like the Milky Way rotate with near-perfect balance, their arms tracing graceful curves that echo the symmetry of a dancer's pirouette. Even the laws of physics themselves seem to respect this cosmic harmony. What works on Earth holds true in distant galaxies, as if the universe signed a contract with itself to stay consistent. But symmetry's real magic lies in how it breaks. Picture a pencil perfectly balanced on its tip. In theory, it's symmetrical, but the slightest disturbance sends it toppling, choosing one direction over another. The universe did something similar moments after the Big Bang. In those first searing microseconds, matter and antimatter should have annihilated each other, leaving behind a sea of pure energy. Yet here we are in a world made of matter. Why? Because symmetry broke, some tiny imbalance, perhaps one extra particle of matter for every billion antimatter particles tip the scales, allowing stars, planets, and eventually us to exist. Physicists call this CP violation, where the delicate mirror between particles and their antiparticles cracks ever so slightly. Without this cosmic imperfection, reality as we know it would have evaporated before it began. Einstein once mused, "God is subtle but not malicious," a nod to how the universe hides its secrets in plain sight, wrapped in layers of symmetry. Consider the Higgs field, an invisible energy blanket that gives particles mass. Its existence was predicted because without it, the equations of particle physics lost their elegant symmetry. When scientists finally detected the Higgs boson in 2012, it wasn't just a new particle, it was proof that symmetry isn't just a pretty pattern. It's a scaffolding holding reality together. Yet for all its power, symmetry isn't omnipotent. The very fact that we exist proves the universe isn't perfectly symmetrical. Neutrinos, those ghostly particles that stream through you by the trillions, might hold the key. They spin only to the left like cosmic corkscrews with no right-handed counterparts. This handedness is another broken symmetry, a clue that the universe has preferences, biases even, and those biases might explain why there's something rather than nothing. So is symmetry the universe's ultimate truth, or just a starting point? The answer might lie in black holes, where gravity warps spacetime into such extreme asymmetry that even light can't escape. Or in quantum entanglement, where particles separated by light years remain mysteriously linked, defying classical notions of balance. Symmetry guides the cosmos, but its fractures, those imperfections, are what make the universe rich, dynamic, and alive. Perhaps that's the deepest lesson. Perfection isn't the goal. It's the cracks in the cosmic mirror that let the light in. At first glance, the universe seems torn between two extremes. On one hand, the clockwork precision of planetary orbits, the flawless symmetry of galaxies. On the other, the explosive randomness of supernova, the turbulent swirls of interstellar gas. How can such chaos and order coexist? Enter chaos theory, the science of unpredictability within deterministic systems, where tiny changes in initial conditions snowball into wildly different outcomes. You've probably heard of the butterfly effect, the idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas weeks later. But here's the cosmic twist. The same principle applies to the birth of galaxies. In the early universe, quantum fluctuations, those tiny, random ripples in spacetime, were the ultimate butterflies, smaller than an atom. These fluctuations should have been insignificant. Yet, thanks to the universe's explosive inflation, they were stretched to cosmic proportions, becoming the seeds for all future structure. A slight overdensity here, an underdensity there, these microscopic irregularities dictated where galaxies would bloom and where voids would sprawl. It's chaos writ large, subatomic randomness sculpting the fate of superclusters. But here's the paradox. While chaos shaped the universe's infancy, the mature cosmos looks anything but disordered. The same quantum noise that spawned randomness also created the cosmic web's eerie regularity, filaments and voids distributed with near mathematical precision. How? Because chaos and order aren't opposites, they're partners. Think of a river up close. It's a frenzy of swirling eddies and colliding currents, but from space it carves a graceful, meandering path. The universe works the same way. Quantum chaos at the smallest scales begets large-scale patterns through gravity's relentless averaging. This duality might hold the key to deeper truths. Take black holes, where chaos reigns at the singularity, a point of infinite density where predictability breaks down, yet their event horizons obey exact equations, their shadows perfectly circular as seen in the first ever image from the Event Horizon Telescope. Even the weather, Earth's classic example of chaos, follows seasonal cycles with dependable regularity. The cosmos seems to whisper that chaos isn't the enemy of order, it's the raw material. Perhaps the most tantalizing idea is that chaos and order are two faces of the same cosmic equation. In mathematics, chaotic systems often hide strange attractors, patterns that emerge from apparent randomness when viewed over time. Could the universe's large-scale structure be its own strange attractor, a stable shape born from primordial turbulence? If so, then the dance of galaxies isn't just a product of chance. It's the inevitable outcome of a deeper logic, where chaos and harmony are threads in the same grand tapestry. And that changes everything, because if the universe can weave order from randomness, then even the most turbulent beginnings might lead to something breathtakingly precise. Imagine the universe as a cup of coffee left on the counter, steaming and swirling at first, then gradually cooling, its energy dissipating into the room until it reaches the same tepid temperature as its surroundings. This slow slide from order to disorder isn't just a kitchen observation. It's the second law of thermodynamics in action, a rule so fundamental it's often called time's arrow. Entropy, the measure of this disorder, always increases over time, but here's the cosmic twist. While entropy dictates that things should fall apart, the universe has somehow done the opposite. From a featureless soup of particles after the Big Bang, it sculpted galaxies, stars, planets, and life itself. How can increasing disorder create such breathtaking complexity? The answer lies in a paradox first posed by physicist Ludwig Boltzmann in the 1800s. If entropy always rises, why did the early universe start with such astonishingly low entropy, a state of exquisite, improbable order? Think of it like finding a perfectly stacked house of cards in a tornado. Boltzmann's own life ended before he could solve this riddle, but modern cosmology offers a clue. The young universe was a searing plasma, hot and dense but remarkably smooth, a state of low entropy because matter and energy were nearly uniform. Gravity, the wild card in this cosmic deck, flipped the script. While most forces disperse energy, gravity concentrates it. A tiny clump in that primordial soup pulled more matter toward it, growing denser, hotter, more ordered in its structure, even as the overall entropy of the universe kept climbing. This gravitational sorting is why we have galaxies instead of cosmic rule. As matter collapsed into stars and black holes, it created steep entropy gradients, regions of high and low disorder next to each other. These gradients are like waterfalls in a river. The drop powers motion, structure, complexity. Stars are entropy engines, converting ordered hydrogen into chaotic heat and light. But in doing so, they forge heavier elements that become planets, molecules, and eventually life. The same principle applies to Earth's ecosystems. Sunlight, a high-energy, low-entropy source, drives photosynthesis, weather, ocean currents, all the messy, beautiful complexity of our planet. Recent theories take this further, suggesting entropy gradients don't just allow complexity, they demand it. In 2014, physicist Jeremy England proposed that life might be an inevitable outcome of matter's tendency to dissipate energy efficiently. A bacterium, for example, absorbs nutrients and radiates heat, speeding entropy's increase more than a lifeless chemical soup would. Apply this to galaxies, and you see a similar logic. Spiral arms channel energy, black holes voraciously convert mass into radiation, and cosmic webs funnel matter into ever more efficient entropy generators. Yet the mystery of that initial low entropy state lingers. Some theorists, like Sean Carroll, argue it points to a deeper reality. Perhaps our Big Bang was just one bubble in an eternally inflating multiverse, where most regions are high entropy chaos, and we simply inhabit a rare, ordered fluctuation. Others, like Roger Penrose, see the universe's beginning as so statistically special that it hints at undiscovered physics, laws that might one day explain why time's arrow had to start sharp. What's clear is that entropy isn't just decay, it's the universe's strange way of building. Without it, there would be no Chinese letter to power stars, no storms to shape atmospheres, no chemical imbalances to spark life. The cosmos isn't fighting entropy, it's riding its current, using the slide toward disorder to carve islands of breathtaking order along the way. And that might be the most profound lesson of all. Chaos and complexity aren't opposites. They're collaborators in the universe's endless dance. What if everything you see, the stars, the galaxies, even the space between them, is just an illusion? Not in the philosophical sense, but in a shockingly literal way. The holographic principle dares to suggest that our three-dimensional reality might be nothing more than a projection, a cosmic mirage encoded on a distant two-dimensional surface. Think of it like a movie screen. The images appear to have depth, but they're really just flat patterns of light. The universe, according to this radical idea, works the same way. All the richness we experience, the texture of a tree, the curve of a planet's orbit, the warmth of sunlight, could be data painted onto the boundary of existence itself. This isn't science fiction. It's a serious hypothesis born from the math of black holes. In the 1970s, physicist Jacob Bekenstein discovered that the entropy, the disorder, of a black hole isn't proportional to its volume, as you'd expect, but to its surface area. It was as if all the information about the stuff inside the black hole wasn't lost but smeared onto its event horizon like ink on parchment. Decades later, string theorists like Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might operate on this principle. Their work led to the AD/S/CFT correspondence, a mathematical bridge between theories in different dimensions. In simple terms, it suggests that a higher dimensional universe like ours could be perfectly described by equations operating on a lower dimensional boundary, like a hologram storing 3D data on a 2D surface. But here's where it gets mind-bending. If the holographic principle is true, then math isn't just a tool we use to describe reality. It is reality. The equations governing that 2D boundary wouldn't merely represent the universe, they'd generate it pixel by pixel, moment by moment. Imagine a cosmic computer running a simulation, except the hardware isn't silicon chips but pure mathematics. The particles, forces, and even space-time itself would emerge from the calculations, like a video game rendering a world in real time. Skeptics, of course, demand proof, and in a way we might already have it. The cosmic microwave background, the afterglow of the Big Bang, shows fluctuations that some researchers argue could be signatures of this underlying code. Others point to quantum entanglement, where particles instantly influence each other across vast distances, as evidence that information is fundamentally non-local, just like pixels on a screen affecting distant parts of an image. Yet the most profound implication isn't about how the universe works, but what it is. If math constructs reality, then the cosmos isn't a place, it's a process. A dynamic, ever-unfolding computation where the laws of physics are the algorithms, and we're fleeting patterns in the output. It's a humbling thought that the stars we romanticize, the atoms we're made of, even the time we measure, might all be shadows cast by equations we're only beginning to glimpse. And if that's true, then the ultimate quest isn't just to understand the universe, it's to read its source code. In the world of quantum mechanics, certainty is a luxury we simply don't have. Forget the predictable orbits of planets or the steady tick of a clock. Here, particles exist in a haze of possibilities, a realm where an electron can be in two places at once or vanish and reappear without warning. This isn't science fiction, it's the bedrock of reality at its smallest scales. Take Schrödinger's infamous cat, locked in a box with a vial of poison triggered by the random decay of a quantum particle. Until you open the box, the cat isn't just alive or dead. It's both, existing in a ghostly superposition of states. It's a thought experiment that exposes the absurdity of applying everyday logic to the quantum world, where probability reigns supreme. But superposition isn't just a quirky lab phenomenon. It's woven into the fabric of the cosmos. Consider the vacuum of space, which classical physics once described as pure emptiness. Quantum mechanics paints a far stranger picture. Even in a perfect void, particles flicker in and out of existence like cosmic static, borrowing energy from the future only to vanish moments later. These vacuum fluctuations aren't just theoretical. They generate measurable forces like the Casimir effect, where two metal plates in a vacuum inexplicably attract each other due to the pressure of virtual particles popping into being around them. This probabilistic chaos might seem like a recipe for cosmic anarchy, yet it's the very engine that shaped the universe. Those tiny quantum ripples in the early cosmos, amplified by inflation, became the seeds for galaxies and galaxy clusters. The same uncertainty that leaves an electron's position undecided also wrote the blueprint for the cosmic web. It's as if the universe rolled dice at the Big Bang, and the outcome was everything we see today. So is reality fundamentally uncertain, or is there a hidden order beneath the quantum haze? Some physicists like David Bohm argued for hidden variables, unseen forces that guide particles in ways we can't yet measure. Others, like proponents of the many worlds interpretation, suggest every quantum possibility branches into a new universe, meaning Schrödinger's cat both lives and dies in parallel timeline. Then there's the pilot wave theory, where particles are pushed by invisible waves that dictate their paths, blending determinism with quantum weirdness. The debate cuts to the heart of what math even is in the context of reality. Are probabilities just our way of coping with ignorance, or do they reflect something deeper? A universe built on chance where randomness isn't a bug but a feature. Quantum mechanics doesn't just challenge our intuition. It forces us to confront whether the cosmos is a clockwork machine with hidden gears or a kaleidoscope of ever-shifting possibilities. And until we crack that riddle, the universe will keep its most profound secrets tucked behind a veil of probabilities, whispering that certainty might be the most uncertain thing of all. Imagine space isn't an empty stage where planets and stars perform. It's more like a trampoline, a flexible fabric that bends and warps under weight. That's the core of Einstein's general relativity, where gravity isn't some mysterious force pulling objects together but the natural curvature of spacetime itself. Picture it this way: place a bowling ball in the center of that trampoline, and it creates a deep well. Roll a marble nearby, and it spirals inward, not because it's attracted to the ball by some invisible string, but because the surface beneath it is sloped. That's how mass behaves in the cosmos. Planets, stars, even galaxies don't just move through space. They mold it, and the resulting curves dictate their paths. Einstein's field equations, the mathematical heart of this idea, are notoriously complex, filled with tensors and symbols that make even physicists pause. But strip away the jargon, and they reveal something breathtakingly simple. Matter tells spacetime how to curve, and spacetime tells matter how to move. This isn't just theoretical poetry, it's the reason your phone's GPS works. Satellites orbiting Earth don't just account for distance, they correct for time itself. Clocks on these satellites tick slightly faster than those on the ground because Earth's mass bends space-time more strongly the closer you are to it. Without relativity's math adjusting for this, GPS coordinates would drift by kilometers within minutes. It's a daily reminder that Einstein's geometry isn't abstract, it's woven into the fabric of our technology. Now zoom out to the cosmic scale, and spacetime's curves become the universe's grand choreographer. Galaxies don't just drift aimlessly, they follow the contours of spacetime like marbles rolling along invisible grooves. When two galaxies collide, a slow-motion dance lasting hundreds of millions of years, it's not gravity tugging them together in the old Newtonian sense. It's their combined mass warping the spacetime between them, drawing them into a spiral embrace. Even light, which travels in straight lines, bends around massive objects, a phenomenon called gravitational lensing that lets astronomers peer around cosmic corners like detectives using spacetime's curves as mirrors. This curvature isn't just about pull, it's about balance. Einstein's equations demand that energy and mass precisely match the shape of spacetime, like an accountant reconciling a ledger. When a star explodes in a supernova, the sudden loss of mass sends ripples through spacetime gravitational waves that radiate outward at light speed, detected millennia later by instruments like LIGO. These waves aren't just signals, they're receipts, proof that the universe's books are always balanced, yet relativity's geometry holds deeper mysteries. Near a black hole, spacetime curves so steeply that it folds over itself, creating a one-way exit ramp from reality. And on the largest scales, dark energy stretches spacetime like taffy, accelerating the universe's expansion in defiance of gravity's pull. It's a reminder that for all its elegance, Einstein's masterpiece isn't the final word, just the best map we have to navigate a cosmos where space and time are anything but flat, static backdrops. They're the dynamic, ever-shifting canvas on which the universe paints its story, and every warp, every ripple, is a stroke in that grand design. String theory dares to propose a radical idea that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings, each oscillation producing a different particle or force. But there's a catch. For this elegant math to work, strings can't just wiggle through the three dimensions we know: length, width, and depth plus time. They require 10 dimensions in total. That's not a typo. 6 extra spatial dimensions, curled up so tightly that even the most powerful microscopes couldn't detect them. Imagine a garden hose viewed from a distance. It looks like a simple one-dimensional line, but up close you see its circular cross-section, a second dimension hidden in plain sight. String theory suggests our universe works the same way, with 6 hose-like dimensions compactified into intricate shapes called Calabi-Yau manifolds. These Calabi-Yau shapes aren't just mathematical curiosities. They might hold the key to cosmic diversity. Picture a guitar string vibrating at different frequencies to produce distinct notes. In string theory, the way these extra dimensions twist and fold could determine everything from the mass of an electron to the strength of gravity. One Calabi-Yau configuration might yield a universe with 4 fundamental forces. Another might generate entirely different physics. It's as if the cosmos has a hidden control panel, its knobs and dials set by geometry we can't yet see. Some theorists even speculate that the values of nature's constants, the speed of light, the charge of an electron aren't arbitrary, but locked in by the topology of these unseen dimensions. Yet for all its beauty, string theory faces fierce criticism. The most glaring issue, testability. To prove extra dimensions exist, you'd need particle accelerators the size of galaxies or energy levels 1 trillion times beyond our current reach. Critics like physicist Lee Smolin argue that if a theory can't be falsified experimentally, it's not science, it's metaphysics. Others counter that indirect evidence might surface, like signatures in gravitational waves or anomalies in quantum entanglement. The Large Hadron Collider once hoped to spot supersymmetric particles predicted by string theory, but so far the detectors have stayed silent. Then there's the landscape problem. String theory doesn't predict one unique universe, but a staggering 10 to the 500 possible versions, a multiverse where every conceivable set of physical laws exists somewhere. To skeptics, this isn't a feature but a flaw. If a theory allows everything, does it explain anything? Nobel laureate Sheldon Glashow likened it to medieval theology, intricate, imaginative, but ultimately untethered from empirical reality. Defenders like string theorist Brian Greene argue that criticism overlooks the field's breakthroughs, from advancing quantum gravity research to inspiring new math tools now used in other sciences. The theory's very ambition, they say, demands patience. After all, Einstein's relativity was once deemed abstract nonsense until eclipses and orbiting stars proved it right. At its core, string theory is a gamble, a bet that the universe values mathematical harmony as much as physicists do. Whether it's the final word on reality or just a stepping stone, one thing's certain: it's reshaped how we think about dimensions, symmetry, and the very fabric of existence. And until those extra dimensions reveal themselves, if they ever do, the theory remains the most tantalizing what-if in modern physics. What if our universe isn't the only one? What if it's just a single bubble in an endless froth of cosmic foam, where every bubble contains its own physics, its own stars, its own version of reality? This is the Multiverse Hypothesis, a dizzying idea born from inflation theory, the notion that our cosmos underwent a split-second exponential expansion right after the Big Bang. But here's the twist: if inflation happened once, why couldn't it happen endlessly? Picture a boiling pot of water where steam bubbles constantly form, expand, and detach. Now imagine each bubble is a universe budding off with its own unique properties, some with stronger gravity, others where time runs backward, or where pi equals exactly 3. In this infinite ensemble, every possible configuration of physical laws would exist somewhere. This isn't just speculative fantasy. The math of eternal inflation leads there unavoidably. When quantum fluctuations drive the inflationary process, some regions of space stop expanding while others continue, spawning new universes ad infinitum. It's like a cosmic photocopier stuck on repeat, churning out variations where even the most improbable laws get their turn. String theory's landscape of possible universes, estimated at 10 to the 500 versions, suddenly finds a home in this sprawling multiverse. Think of it as a library where each book is a self-contained universe, and we just happen to inhabit one where the constants allow galaxies, planets, and life. But does this solve the mystery of fine-tuning the eerie precision of our universe's laws that permit existence, or just kick the can down the road? Proponents like Max Tegmark argue it's the ultimate answer. In an infinite multiverse, universes with life-friendly laws are inevitable, even if they're statistically rare. No divine architect needed, just probability playing out on a cosmic scale. Critics fire back that this is a cop-out. Philosopher David Albert compares it to explaining why your car was stolen by positing an infinite parking lot where every possible theft occurs somewhere. It doesn't explain why this universe works, it just asserts that somewhere, somehow, one must. The debate cuts to the heart of science itself. Is the multiverse a testable theory or a philosophical escape hatch? Some point to potential fingerprints, like cold spots in the cosmic microwave background where other universes might have bumped into ours. Others, like physicist Paul Steinhardt, dismiss these as wishful thinking, arguing that unfalsifiable ideas risk turning cosmology into metaphysics. Yet the multiverse lingers because it confronts a deep unease. Our universe's laws feel improbably perfect, like a lock with a billion possible combinations that just happens to open on the first try. The multiverse offers a way out of this existential vertigo, not by solving the puzzle, but by making it vanish into a sea of infinite possibilities. Whether that's profound or merely poetic, one thing's certain: the idea pushes us to the edge of what science can even ask, let alone answer. And that's where the real adventure begins. Imagine tweaking just one number in the universe's code, making gravity slightly stronger or the electron's charge a fraction weaker. Suddenly, stars might never ignite, atoms could fail to bond, and life as we know it would be impossible. Yet here we are, in a cosmos where the constants align with eerie precision, as if the universe had us in mind from the very beginning. This is the Anthropic Principle in its simplest form, the idea that the laws of physics appear fine-tuned for life because, well, we're here to observe them. If they weren't just right, we wouldn't exist to ponder the question at all. It's less a theory than a tautology, a cosmic version of the survivor's bias, where the mere fact of our existence filters the possible universes down to the habitable ones. But does this mean the universe was designed for life, or is it just a statistical fluke? Enter Lee Smolin's audacious alternative, cosmic natural selection. Smolin, a theoretical physicist, proposed that universes might evolve like biological species, with black holes acting as cosmic wombs. Here's how it works. When a black hole collapses, the extreme conditions at its singularity could spawn a new universe with slightly tweaked physical constants. Over countless generations, universes that produce more black holes, those with physics favoring stellar collapse, would dominate the multiverse landscape. In this scenario, our universe isn't special. It's just one of many iterations optimized for black hole production, with life as an accidental byproduct. It's Darwinism scaled up to the cosmos, where survival of the fittest means survival of the most fecund singularities. Critics pounce on this idea's untestability. How would we ever observe these sibling universes, let alone measure their physics? And why would black holes, of all things, be the universe's reproductive mechanism? Yet Smolin's hypothesis forces a crucial question. If we dismiss fine-tuning as mere chance, what's the alternative? The multiverse offers one answer: an infinite array of universes where every possible combination of constants plays out. In that vastness, a life-friendly universe becomes inevitable, no design required. But this just shifts the mystery. Why does any mathematical framework permit life at all? Perhaps the most unsettling possibility is that our math isn't universal, it's parochial. The constants we measure might not be fundamental truths but local bylaws, like the climate of a single island in an endless archipelago of realities. String theory's landscape of possible universes suggests as much, with each version governed by different Calabi-Yau geometries. In some, gravity crushes atoms instantly. In others, electromagnetism is too weak to forge molecules. Ours, by sheer luck, landed in the Goldilocks zone, yet even this explanation feels incomplete. It doesn't address why mathematics, a human invention, maps so perfectly onto cosmic laws. Einstein once wondered whether God had any choice in creating the universe. Could the laws we see be the only possible consistent ones? Some theorists, like Max Tegmark, argue that math isn't just a tool to describe reality. It is reality, with every coherent structure existing somewhere in the multiverse. In this view, the Anthropic Principle isn't about selection but about location. We find ourselves in a mathematical structure where our kind of consciousness can arise. The debate reveals a deeper tension in cosmology. Are we the protagonists of the universe's story, or just bit players in a drama too vast to comprehend? The Anthropic Principle, for all its philosophical wrinkles, reminds us that science isn't just about how things are, it's about why we're here to see them. And that question, more than any equation, might be the ultimate frontier. What if everything around you, the stars, the laws of physics, even your own thoughts, were lines of code in an unfathomably advanced simulation? Philosopher Nick Bostrom's simulation hypothesis isn't just sci-fi speculation, it's a serious statistical argument that hinges on three unsettling possibilities. Either civilizations like ours almost always go extinct before reaching technological maturity, or they lose interest in creating ancestor simulations, or we're almost certainly living in one right now. The logic is chillingly simple. If future civilizations develop the computing power to simulate conscious minds, and they have any desire to run such simulations, the number of simulated beings would dwarf the number of original ones. Statistically speaking, the odds that we're the rare organic originals are vanishingly small. But how would we even begin to test such a radical idea? Some researchers suggest looking for cosmic glitches, places where the supposed simulation cuts corners to save processing power. Quantum indeterminacy, where particles lack definite properties until observed, could be one such shortcut. Why render every electron's position in full detail when you only need to calculate it when someone looks? Even the speed of light, nature's ultimate speed limit, might be a buffer preventing the simulation from overloading, like a processor throttling performance to avoid crashing. The infamous double-slit experiment, where particles act as waves unless measured, feels eerily like a video game that only renders graphics where the player is looking. Then there's math itself. The universe's uncanny reliance on mathematical laws, from the Fibonacci sequence in galaxies to pi in black holes, could suggest that reality is fundamentally computational. In a simulation, math wouldn't just describe the rules, it would be the rules. The gravitational pull between stars, a physics engine calculating forces. The chemical bonds in your cells, subroutines executing predefined algorithms. Even randomness, like radioactive decay, might be pseudorandom noise generated by deterministic code, much like the random levels in a procedurally generated video game. Critics counter with Occam's razor: why invent cosmic programmers when our universe's laws stand fine on their own? Others argue that simulating consciousness is impossible in principle. You can simulate a rainstorm without creating actual wetness, so why assume simulated minds would experience qualia? And then there's the meta problem. If we're in a simulation, who's to say the simulators aren't themselves simulations? Turtles all the way down. Yet the hypothesis lingers because it reframes the deepest questions. If math is the simulation source code, then physicists aren't just uncovering nature's laws, they're reverse engineering the programming of reality. It also casts fine-tuning in a new light. Maybe our universe's constants seem dialed to perfection because someone or something set them that way. Even time's arrow could be a memory management strategy, with the past compressed to save storage and the future left uncomputed until needed. Whether you find the idea thrilling or terrifying, it forces a profound shift in perspective. If the cosmos is a calculation, then every galaxy, every atom, every fleeting thought is part of an equation we're only beginning to glimpse. And that raises the ultimate question. If we're living in someone else's simulation, what's running ours? Occam's razor. The idea that the simplest explanation is usually the right one has guided scientists for centuries, slicing through convoluted theories like a blade through fog. But the universe doesn't always play by tidy rules. Take Johannes Kepler, who spent years trying to force the planet's orbits into perfect circles, convinced that divine geometry demanded symmetry. The data resisted until he reluctantly embraced ellipses messier, less perfect, but undeniably accurate. His breakthrough wasn't just a victory for observation over dogma, it revealed a deeper truth. Nature often prefers functional complexity over elegant simplicity. Now fast forward to modern cosmology, where dark matter taunts us with a similar dilemma. The simplest explanation, that 85% of the universe's mass is invisible, intangible, and detectable only through its gravitational pull. It's a staggering proposition, like claiming every city is full of ghosts just because doors keep swinging open. Yet the evidence is overwhelming. Galaxies rotate too fast, light bends around empty space, and the cosmic web's structure defies gravity's known laws without some unseen anchor. Occam's razor would suggest we're missing something obvious, that dark matter is a placeholder for a simpler theory we haven't yet grasped. Enter the challengers, modified gravity theories like modified Newtonian dynamics, which tweak the equations of motion to explain galactic rotations without invoking invisible matter. At first glance, it's the epitome of Occam's ideal: no hidden variables, no shadowy particles. But here's the rub. Works beautifully for individual galaxies, yet stumbles when applied to galaxy clusters or the cosmic microwave background's intricate patterns. Like Kepler's circles, it's elegantly simple but incomplete. The universe, it seems, would rather layer on complexity than surrender to our craving for neatness. This tension isn't just academic, it's a window into how science evolves. Sometimes the simplest answer isn't the one that ignores complications, but the one that embraces them. Dark matter might feel like a clumsy fix, but until a theory emerges that explains all the evidence without it, we're stuck with the messy reality. After all, Kepler's ellipses were once seen as a compromise too. Today, they're celebrated as the fingerprints of a universe that writes its own rules, whether we find them beautiful or not. The lesson: when cosmic complexity defies Occam's razor, perhaps it's not the universe that needs simplifying but our expectations. In 1931, a quiet revolution unfolded not in a laboratory or observatory, but on a mathematician's notepad. Kurt Gödel, then a 25-year-old prodigy, proved something astonishing. Even in the most rigorous logical systems, there will always be truths that cannot be proven. His incompleteness theorems shattered the dream of a perfect, all-encompassing mathematical framework, one where every true statement could be derived from a set of axioms. Instead, Gödel revealed that any system complex enough to describe basic arithmetic is either incomplete, containing true statements it can't prove, or inconsistent, allowing contradictions. It was like discovering that every language, no matter how rich, has thoughts it cannot express. Now fast forward to cosmology, where physicists chase their own holy grail, a theory of everything that unifies quantum mechanics and general relativity. Gödel's shadow looms large here. If even arithmetic has unprovable truths, could the universe itself contain phenomena that forever elude our equations? Stephen Hawking wrestled with this very question. Late in his career, he conceded that a complete physical theory might need to include observers, conscious beings who measure and interpret, as fundamental components, not just accidental byproducts. It's as if the cosmos operates like a locked book, with some pages readable only when someone attempts to turn them. Consider black holes. Their singularities, points of infinite density, are where our current laws of physics break down catastrophically. General relativity predicts them, but quantum mechanics balks at the idea of infinities. Most theorists assume this clash signals a limitation in our theories, not reality itself. But what if it's more profound? What if singularities are cosmic manifestations of Gödelian incompleteness, truths that cannot be resolved within our current mathematical language? The event horizon might then be more than a physical boundary. It could represent the edge of what's provable, a mathematical horizon beyond which certain truths remain forever veiled. This isn't just about black holes. The very fabric of spacetime might encode unprovable statements. Take dark energy. We can measure its effects, but its nature resists explanation. Is this because we lack the right tools, or because dark energy is to cosmology what Gödel's unprovable truths are to mathematics? A feature, not a bug. Some researchers, like physicist David Deutsch, suggest that quantum weirdness, with its probabilities and observer dependence, might be the physical analog of logical incompleteness. In this view, the universe isn't hiding its secrets. It's fundamentally built to keep some of them. Yet there's an alternative interpretation, one that turns despair into wonder. If the cosmos has inherent limits to what can be known, it doesn't mean our quest is futile. Gödel's theorems didn't end mathematics. They revealed its infinite depth. Similarly, a universe with unanswerable questions might be richer, not poorer. Hawking's suggestion to include observers hints at a radical idea. Perhaps the universe isn't a static puzzle to be solved, but a dynamic interplay between physical laws and the minds that perceive them. The equations we've discovered, from Newton's gravity to Einstein's relativity, aren't just descriptions. They're collaborations, shaped as much by the universe's structure as by our way of questioning it. So is the universe's math incomplete, or is completeness itself the wrong thing to seek? After all, a system that could explain everything would leave no room for curiosity, no space for the thrill of the unknown. Gödel's theorems, far from being obstacles, remind us that the cosmos is more than a set of solvable equations. It's an open-ended story with chapters we're still learning to read, and perhaps some meant to remain forever unwritten. In the quantum realm, reality seems to wait for an audience before deciding what to be. Take the classic double-slit experiment. When unobserved, electrons behave like waves, creating interference patterns as if they're in multiple places at once. But the moment a detector is introduced to measure which slit they pass through, they snap into crisp, localized particles. It's as if the act of observation forces the universe to pick a side, a phenomenon physicists call the collapse of the wave function. This isn't just laboratory curiosity. It suggests something profound. At its core, reality might not be a fixed stage but a shimmering cloud of possibilities, crystallizing only when something or someone takes a look. But who or what counts as an observer? A human scientist scribbling notes, a photon-detecting machine, or could it be any interaction that leaves a mark on the world? The debate cuts to the heart of quantum mechanics' strangest riddle. Some interpretations, like the Copenhagen school, argue that consciousness plays a unique role in shaping reality. Others, like the decoherence camp, insist that any interaction with the environment, a stray air molecule, a cosmic ray, can collapse probabilities without needing sentient beings. Yet even here, the line blurs. If a falling tree triggers vibrations in the ground, does the soil observe the event? The universe, it seems, keeps its receipts, recording every interaction in ways we're only beginning to decode. This puzzle takes on cosmic proportions when you consider physicist John Wheeler's famous phrase, "it from bit." Wheeler proposed that information, not matter or energy, might be the universe's true currency. Every particle, every force could be a kind of cosmic data point, with reality itself emerging from a vast network of yes-no questions, binary choices etched into the fabric of spacetime. In this view, black holes aren't just gravity wells but ultimate information processors. their event horizons encoding data like celestial hard drives. Even the Big Bang might have been less an explosion than a computation, booting up the cosmos by generating its first bits. The implications are dizzying. If information underpins reality, then observers aren't passive witnesses but active participants, their measurements stitching the cosmic tapestry together one thread at a time. This doesn't mean humans are dreaming up the universe. Wheeler's ideas are far more subtle. Rather, the act of observation might be a kind of cosmic handshake where the universe reveals itself through the questions we ask. Quantum experiments already show that the choice of what to measure, a particle's position or its momentum, changes the answer you get. Extend this to cosmology, and you're left wondering, does the universe need life to fully exist? Skeptics push back hard. They argue that equating observation with consciousness is a slippery slope, veering into pseudoscience. After all, stars and galaxies existed for billions of years before life appeared. Were they in some unreal quantum fog until the first sentient creature looked up? Most physicists prefer less anthropocentric explanations, like the many worlds interpretation, where every quantum possibility branches into a parallel universe, no observers required. Yet the mystery lingers. Whether or not consciousness plays a starring role, the undeniable truth is this: the universe seems to keep score. Every interaction, every measurement leaves an imprint on the cosmic ledger, shaping what we call reality. And that raises a humbling possibility. The math we use to describe the cosmos might not just be a human invention. It could be the universe's native tongue, a language it speaks every time a particle spins, a star burns, or a curious mind peers into the night sky, asking, "What's out there?" In the end, the answer might depend on who's asking. We think of time as a constant and unstoppable river flowing from past to future. But what if time isn't fundamental at all? What if it's more like a mirage, a side effect of deeper mathematical relationships lurking beneath the surface of reality? This radical idea comes from an unlikely pairing: thermodynamics and quantum gravity. Take entropy, the measure of disorder that gives us time's arrow. In the early universe, entropy was incredibly low, a state of near-perfect order. As the cosmos expanded, entropy climbed, creating the one-way gradient we experience as time. But here's the twist: entropy isn't a force or a substance. It's a statistical property emerging from countless particles interacting. So if time arises from entropy, and entropy arises from particle behavior, then time itself might be a kind of collective illusion, a story the universe tells itself as things get messier. Quantum gravity takes this further, suggesting time might vanish entirely at reality's most fundamental level. In loop quantum gravity, one of the leading candidates for unifying quantum mechanics and general relativity, spacetime isn't smooth and continuous but granular, woven from tiny, indivisible loops. At this scale, the equations describe a timeless network of relationships, a cosmic frozen snapshot where before and after have no meaning. Time only emerges when you zoom out, like the illusion of motion in a flipbook. Similarly, string theory's holographic principle implies that time, like space, could be a projection from a timeless, lower-dimensional boundary. It's as if the universe is a 2D movie screen, and time is just one of the dimensions our brains interpret as real. Nowhere is time's fluidity more striking than at the edge of a black hole. As you approach the event horizon, time doesn't just slow, it stretches infinitely thin from an outsider's perspective. To a distant observer, a falling astronaut would appear frozen, their last moments smeared across eternity. Yet for the astronaut, time flows normally until the end. This isn't just relativity at work, it's a clue that time might be relational, a local effect rather than a universal backdrop. even stranger inside a black hole singularity, time and space swap roles. What was once a direction in time becomes a direction in space, and vice versa, as if the universe itself forgets which is which at the edge of existence. The implications ripple outward. If time emerges from deeper physics, then our intuitive sense of past, present, and future could be a kind of cosmic user interface, a simplified dashboard for navigating a reality far stranger than we perceive. It also raises haunting questions. Without time as a fundamental ingredient, what does change even mean? How does causality work? Some theorists propose that causality itself emerges from entanglement, the quantum links binding particles across space and perhaps across time. Others suggest that what we call time is just a particular slice through a higher dimensional reality, like a single frame selected from a reel of film. This isn't just philosophy. Experiments with entangled particles and quantum clocks are testing these ideas, probing whether time remains coherent at the smallest scales. Early hints suggest it might not, that beneath the tick of every clock, the universe hums with timeless mathematical relationships. If true, it would rewrite our origin story. The Big Bang wouldn't be the beginning of time, but the moment time crystallized from something deeper, something eternally present. And that changes everything, because if time is an emergent property, then the universe isn't just unfolding in time. It's weaving time itself into existence, stitch by mathematical stitch. Human mathematics, for all its elegance, might be just one dialect in a cosmic conversation, a rough translation of laws written in a language we don't yet understand. Think of it like a fish trying to describe water. Immersed in it since birth, the fish has no concept of wetness, no word for fluid dynamics. It might invent equations to predict currents or tides, never realizing these are just surface ripples of something far deeper. Our math could be just as provincial, a tool shaped by the narrow slice of reality we've experienced, blind to frameworks beyond our perceptual and cognitive limits. Consider how our number system relies on base 10, likely because we evolved with 10 fingers. But what if the universe counts in a different base or in no base at all? Even our most advanced theories, like quantum mechanics and general relativity, rely on mathematical constructs that might be approximations, like using Newton's laws to describe a falling apple while missing the curvature of spacetime beneath it. The discrepancies in our model's dark matter's gravitational pull, quantum entanglement's spooky connections, could be hints that we're not speaking the universe's native tongue. This is where M-theory enters, physics' boldest attempt to transcend these limits. Imagine trying to describe a symphony using only the language of a single instrument, say, a violin. You could capture melodies but miss the harmonies of cellos, the resonance of brass. M-theory proposes that our current theories, string theory's various versions, supergravity, are like those isolated instruments, all fragments of a grander composition. By unifying them into an 11-dimensional framework, M-theory hints at a mathematical mother tongue that could describe everything from quarks to quasars without contradictions. Yet even this ambition stumbles. M-theory's equations remain unfinished, its predictions untested, like a Rosetta Stone missing half its inscriptions. The challenge isn't just technical, it's existential. If the cosmos operates on mathematical principles beyond our intuition, higher dimensional algebras, non-commutative geometries, could we ever comprehend them? Our brains evolved to navigate a three-dimensional world, to avoid predators and find food, not to intuit Calabi-Yau manifolds or holographic entropy. It's like an ant trying to grasp the internet. The scale and structure lie outside its evolutionary toolkit. Yet history offers glimmers of hope. Each time we've hit the limits of our math, negative numbers, irrational numbers, imaginary numbers, we've expanded the language. When Einstein needed to describe curved spacetime, he borrowed Riemannian geometry, a once useless branch of math. The universe seems to reward those who invent tools before they know the job. Perhaps M-theory, or some yet unnamed framework, will be the next leap, not just a new equation, but a new way of seeing. Until then, we're like scribes copying a text in a forgotten script, trusting that the gaps we see aren't flaws in the universe, but in our translation. The universe generates data at a scale that would make even the most powerful supercomputers blush. Billions of galaxies, trillions of stars, and uncountable particles interacting in ways that defy simple equations. For centuries, humans have tried to decode this deluge with pencil and paper math, but we're hitting a wall. Enter artificial intelligence, the first tool in history capable of sifting through cosmic haystacks to find needles we didn't even know existed. Take the Euclid mission, the European Space Agency's ambitious project to map the dark universe. Over 6 years, its space telescope will image billions of galaxies, measuring their shapes and positions with microscopic precision. The dataset will be so vast, petabytes of raw images, that traditional analysis would take decades. But Euclid's secret weapon is machine learning, algorithms trained to spot the subtle distortions in starlight caused by dark matter's gravitational tug. These AI systems don't just process data faster, they detect patterns invisible to human eyes, teasing out the invisible scaffolding of the cosmos from noise that would have baffled Einstein. Yet AI's role goes beyond crunching numbers. At the Perimeter Institute, researchers are feeding neural networks simulated universes governed by different physical laws, then tasking them with reverse engineering the underlying equations. In one experiment, an AI deduced Newton's laws of motion from raw orbital data alone, no prior physics knowledge given. Now imagine scaling this up to unsolved mysteries like dark energy. Traditional methods rely on human intuition to propose equations, then test them against observations. AI flips the script. It lets the data propose the equations, uncovering relationships that might never occur to a physicist bound by classical thinking. Some call this automated science, where algorithms become co-investigators, hinting at structures beyond our conceptual reach. But the real revolution might be yet to come. Quantum machine learning, still in its infancy, could one day analyze cosmic phenomena in ways that merge quantum weirdness with cosmic scale. Picture an AI that doesn't just process data, but exists in a quantum superposition, evaluating countless theories simultaneously. Or consider generative models like GPT, but trained on astrophysical papers and datasets, a system that could propose entirely new cosmological models by remixing the universe's known rules into uncharted combinations. The risk, of course, is ending up with answers we don't understand. An AI might spit out an equation that perfectly predicts galaxy rotations but relies on variables without clear physical meaning. Would we trust a black box's math if it contradicted centuries of human-derived theory? The stakes go beyond astronomy. If AI can decode the universe's hidden arithmetic, it might reveal whether math is invented or discovered, whether we've been uncovering eternal truths or just crafting useful approximations. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will soon flood scientists with 10 times more data than Euclid, making AI not just helpful but essential. The cosmos isn't waiting for us to catch up. It's streaming its secrets in a language we're only beginning to translate. And this time, we might not be the ones doing the translating. The equations of tomorrow could be written in a dialect only machines understand, with us peering over their shoulders, straining to comprehend the universe's next chapter. Knowledge has always been a double-edged sword. Fire warmed our ancestors but also burned their villages. Today, as we stand on the brink of deciphering the universe's deepest equations, we face a similar dilemma. What happens when humanity unlocks not just the secrets of atoms or stars, but the very source code of reality? Imagine a civilization that learns to tweak the fundamental constants, adjusting the strength of gravity or the charge of an electron like sliders on a cosmic control panel. The power to reshape physics could let us engineer stars, halt entropy, or even spawn new universes, but history warns us such power rarely stays benevolent. The same equations that might one day let us harness dark energy could also become weapons of unimaginable destruction, unleashing forces that make nuclear bombs seem like firecrackers in comparison. Carl Sagan once called understanding a kind of ecstasy, a celebration of our place in the cosmos. His vision was one of pure wonder, a universe where knowledge lifts humanity higher, binding us together in shared awe. And there's truth in that. Every equation we've decoded, from Newton's gravity to Einstein's relativity, has expanded not just our technology but our empathy, revealing how deeply we're connected to the fabric of existence. The Hubble Deep Field image didn't just teach us about galaxies, it humbled us, shrinking earthly conflicts into cosmic insignificance. But Sagan also warned of technological adolescence, that precarious phase where a species gains great power without the wisdom to wield it. The stakes couldn't be higher. Consider the Large Hadron Collider, where physicists recreate conditions a trillionth of a second after the Big Bang. Before its launch, fringe theories speculated it might spawn a black hole that could swallow Earth. The risk was infinitesimal but not zero. Now scale that up. If we ever discover how to manipulate the Higgs field, the quantum vacuum, or spacetime itself, the margin for error shrinks to zero. One miscalculation, one reckless experiment, and we might not just destroy ourselves, we could unravel the local universe. Yet refusing to seek knowledge isn't the answer. The universe's math isn't just a tool, it's a mirror. It reflects back who we are: curious, flawed, capable of both creation and destruction. The real challenge isn't whether we can decode these equations, but whether we can mature fast enough to handle them responsibly. That means building safeguards not just in labs, but in our collective psyche. It means prioritizing collaboration over competition, wisdom over profit, and long-term survival over short-term gain. Perhaps the most ethical stance isn't fear or blind optimism, but something in between, a humble recognition that some truths come with obligations. The same cosmic arithmetic that lets us measure starlight also binds us to every atom in the cosmos. If we're truly made of star stuff, as Sagan said, then tampering with the universe's math isn't just playing with forces, it's playing with ourselves. And that demands not just brilliance but reverence. The universe has waited 13 billion years to be understood. We owe it the patience to be worthy of that understanding. From the Babylonians tracking planetary motions to AI sifting through dark matter's fingerprints, our quest to decode the universe's arithmetic has been a story of relentless curiosity, a dialogue spanning millennia, where each generation adds a new verse to the cosmic equation. What began as sacred numerology etched into clay tablets has blossomed into a search for the universe's source code, a journey where every discovery peels back another layer of mystery. The numbers we once thought were divine whispers: pi in the orbits of planets, the golden ratio in spiral galaxies, primes in quantum states, now hint at something even more profound. That math isn't just a tool we use to describe reality. It might be reality, the invisible scaffolding holding existence together. Yet for all we've uncovered, the cosmos retains its elusiveness. Dark matter evades our detectors, Dark energy defies our equations, and the quantum realm laughs at our intuition. But here's the beautiful paradox. The universe's math is both a map and the territory. It guides us to new horizons while reminding us how much lies beyond the edge of the chart. Every time we think we've cracked the code, like Kepler swapping perfect circles for ellipses, or Einstein trading Newton's gravity for curved spacetime, the universe reveals another puzzle, another zero in the quantum vacuum, another fractal twist in the cosmic web. This isn't a failure, it's an invitation to wonder, to question, to stand under the night sky and feel the thrill of knowing we're part of something vast and mysterious. As Carl Sagan once said, we are a way for the cosmos to know itself. Our equations, our telescopes, even our stumbling hypotheses are how the universe wakes up to its own beauty. So keep looking up, keep asking why, and remember, the most profound discoveries often begin not with answers but with awe. Share your thoughts below. What part of this cosmic arithmetic leaves you breathless? The conversation, after all, is just